All right, we're going to talk about two series now. Two series are just a special case of regular factorial models where each of the factors specifically has two levels. So there's kind of a whole way notation that we use when we work with two series in particular. They are distinct from other factorials, again, only in that they have two levels rather than multiple levels, more than two. When we have, say, k factors that are all two series, we would use the shorthand 2 to the k design. This is important notation, as later we'll be talking about fractional factorials, and this kind of notation is going to come up. We could also talk about 3 series, 4 series, 5 series. We're not emphasizing that here because 2 series are just far more common and useful. So 2 to the k design is that smallest k factor design we could consider. It's a very common design, and there's lots of specialty notation and methods associated with these 2 series designs in particular. 2 series are so common particularly because we often have designs where the factors have natural levels such as plus or minus, on or off, low or high. And we can code these using the levels 0 for like low or off, and then 1 for high or on. You can even think back to our ultimate tomato challenge. Think about for a moment, is that a 2 series? If so, how would you describe that? What is the k in particular? We might talk about that in class. Okay, so let's talk about some of the notations used here. If we have k factors, we might in particular have like 3 factors, a, b, and c. So we'd have 3 factors, which would be a 2 to the 3, because k would be equal to 3. So a 2 to the 3 design would have 8 treatments. Okay, these would be all the unique combinations of the 2 levels of a, b, and c. So if a factor is low or off, we call it 0, and if it's high or on, we call it 1. So for example, 0, 1, 1 here would have a low, b high, c high. We could also use an alternate notation where the lowercase letter of the factor gets used to indicate that it is at the high level rather than the 1 being used. So for example, in this case, bc would indicate that b and c are both high, just like up here, and that 1 is low. So this notation would be equal to this notation, or denoting the same effect, I should say. I don't favor this one as much simply because where did we use lowercase before? It was when it would indicate the number of levels. So maybe lowercase a minus 1 would be the number of degrees of freedom for a main effect factor a. So I think that gets a little confusing. I actually remember being thrown off by that for a few seconds and then realizing what they meant by that notation, but I don't think it's good to reuse notation, just my preference. If you do use this though, it's okay. If you use this method, 1 here is equivalent to 0, 0, 0. It's when all the factors are at their low level. Okay, so we can use either notation in class. I don't know, we'll see which one ends up being preeminent. So the standard order of all the factors low, and then it enumerates with, you could go in really any order, but it kind of makes sense to go A, B, and then C. Okay, so take a look. Make sure you understand how these 2 notations align and how they work. Please ask me in class if you have questions. Okay, so each main effect or your interaction is going to have a single degree of freedom. Think of it this way. Because we are dealing with 2 series, meaning there's 2 levels, we actually have 2 minus 1 degrees of freedom for each main effect. Then the interaction, which is just the multiplication of the main effect degrees of freedom, would be 1 times 1, which gives you again a 1. So every effect, I don't care how high order it is going to have a degree of freedom 1. That presents some unique opportunities, but also some unique challenges. One nice thing is because of this, we can represent these contrasts as a table of plus and minus signs, plus ones, plus minus ones, in other words. If we know the signs of the factors, then we can get the signs for an interaction effect using element-wise multiplication for the signs of the factors in the interaction. Okay, so let's play this out. For example, we should fully enumerate this table, but if you recall, once we know the signs of those factors, we get the signs by just using the signs in the factors. So, for example, if we fill in the blank with AB, okay, here, when the main effect for A is high and the low effect for B is indicated, then the interaction will just be the plus times the minus and give us a minus for AB. Notice that when we take all three, the plus for A, the minus for B, the minus for C, we get a plus sign for the three-way interaction between the factor levels, or the factors, I should say. When does this three-way interaction become negative? In cases, in particular, where either all three main effects are negative, or two are positive and one is negative. For example, the effect AB is the one where A is high, B is high, C is low, and hence the ABC interaction is negative. Similarly, AC or BC. All right, you can see in the book that he goes into a little bit more detail, but he actually does this for a higher order, if I recall. I think in this chapter, that may have been fractional factorials, but you can see it fully enumerated. One benefit of doing it this way is that all of our effect contrasts are going to be orthogonal. And what does it mean when our contrasts are orthogonal? Take a moment, we'll review this because this is so important. Orthogonal contrasts contain information about the variation that is non-overlapping. So we can best partition up the sources of variability in our experiment by using orthogonal contrasts. It's not that we always have to have orthogonal. Sometimes that just doesn't fit our research questions, right? But when you can make up a set of orthogonal contrasts, it's to your advantage because you're going to get the most bang for your buck. Okay, and they operate independently consequently because they have non-overlapping information, hence are independent sets of contrasts. So the result that you get for one orthogonal contrast, for one contrast that's orthogonal to another, will not depend in any way with the result from others. Okay, so under our null hypothesis of no effect, those effect estimates are going to be independent. They have a mean of 0 and a constant variance. So we can really easily describe, under all assumptions being met of our ANOVA model, this sampling distribution under the assumption of the null. Then we can say that all significant effects of any order, because these all follow that same sampling distribution, are going to be outliers in a normal probability plot. Okay, Gary recommends a half normal. I don't really care either way. Our software, though, does a QQ normal probability plot, so we'll probably just use that. This approach assumes that most effects are null and only a few are going to be significant, outlying. And this is very important because we have no estimate of pure error in this case, because each effect, if you recall, has a single replication. And so when we have only that single replication, we have no estimate for that pure error. And so we need to be able to detect these outliers using an alternate method. Okay, so a statistician, I think his first name was Richard, if I remember right, Dr. Lenth, used a pseudo-standard error in an attempt to go beyond kind of the identification of outliers in 2 to the k factorials. Going beyond that, I know it when I see it criterion that we tend to often use. The PSE, or pseudo standard error method, assumes that most effects are going to be null, and then uses the bulk of the smallish effects to then go back and estimate that error. So you can kind of think about it as being summarized in these 3 steps. You set aside all effects larger than 3.75 times the median of the absolute value of the effects of your model. So those would be called just large effects. Just a way to measure when you're more than 3.75 times that median, that gives you pretty good evidence that it is a larger than average effect, whether it be a large positive effect or a large negative, hence the absolute value. Then the PSE is going to be 1.5 times the median of the remaining absolute effects. Okay, so those are kind of deemed the most common. Okay, so the PSE is just going to be 1.5 times the median of those that kind of fall within the normal range. And I'm not saying normal is a normal distribution, the regular range, I should say. Then the PSE as the denominator for a t-test on the effects with, and here's where the degree of freedom comes from, it's going to be that 2 to the k minus 1 divided by 3. Okay, there's a little bit of explanation more about this test, but I'm not going to spend a lot of time. In practice, I think you'll see both that kind of eyeing the outliers and thinking which ones look like outliers from your model, and then using the pseudo standard error approach is also fairly common. Now, if your data is 2 series and all are going to be 0 except for a non-zero value, then your factorial effects are all equal in absolute value. This gives you flat areas on your, well, kind of reflections on your full normal probability plot, and flat spots on your half normal, and can indicate that you have an outlier or some sort of interaction. We'll see if this comes up. I can't really remember if it comes up in the notes or book. Whoop, I went the wrong way, I just realized. Okay, so let's take a look at an example following this, and then we'll move on to using these designs with blocks.